1. Here we go. All right, we're live. All right. So we learned the alternating series test yesterday, and the alternating series is simply a series that does what? Alternates. And what does that mean? Negative to positive or positive to negative on consecutive terms. Consecutive terms. Okay. And there are two qualifications. Part of what we need to be able to do at the end is look at a series, know which test to use, and then for each test, you have to be able to formulate the arguments. There's some necessary preconditions. So the alternating series test, was it a one-way test or a two-way test? It's a one-way test. It's only a test for convergence. And the two requirements were the limit of the rule of sequence for the nth term goes to 0, and it gets smaller eventually at some point. There you go. Okay. So we're going to look at this little idea here right now, and this is a very important idea. So remember, the only series right now for which we can find the exact value is which type? Geometric, right? But there is hope for other series that don't have formulas to find the sum. You can actually trap the sum between two numbers. Okay, you can trap it. You don't know where it is in that interval, but you know it's not going to be outside the interval. So in order to do that, we have to find what's called the remainder, or it's also called the error bound. They're pretty much interchangeable, remainder or the error bound. If you've taken statistics, it's kind of like a margin of error, like when you do a confidence interval, right? Okay, so but here's what it is for the alternating series. Suppose that we have an alternating series that satisfies those two conditions. That is, that it converges, okay? If the series then has a sum S that we're really after, we want the actual sum, then we know that the remainder, using n terms as our sum approximation, that's what n means, we're going to find the remainder, adding up the first n terms, is going to be equal to the actual sum minus the partial sum. Okay, now that is going to be less than or equal to a sub n plus 1. What the heck does all this mean? This just means that the remainder, or the error bound, is going to be less than or equal to the first unused term. So in other words, if I have an alternating series, I can add up the first 4 terms to get an approximation of the sum. Since I use the first 4 terms, I know then that that sum has to be within whatever the value of the 5th term is, okay, from that number. And we're looking at absolute values here because we're working with magnitudes. All right, if I add up the first 10 terms to get an approximation of the actual sum, I know that that sum has to be within whatever the value of the 11th term is, right? So a sub n plus 1 is the first unused term, okay? And we call that the remainder or the error bound. You can actually then trap it in an interval. If you take your partial sum of the first n terms and you subtract the remainder, the first unused term, you get the lower bound. And if you take your partial sum and add the remainder, the first unused term, you get your upper bound, okay? And of course, just like a margin of error, the more terms you add, the smaller your interval is going to be, right? You're going to trap it in a increasingly smaller interval. But it's always a trade-off between how many terms do we want to add and how accurate do we want to be, right? Because it gets a little bit more tedious to keep adding more and more terms. Now, calculators, of course, can make quick work of that. But let's see what I'm talking about. Example 18. Approximate the sum, the sigma from n equals 1 to infinity of negative 1 to the n minus 1 over n factorial, okay, by using its first 6 terms, okay, and then find the error bound. So first of all, is this an alternating series? Yes. How do we know? Negative 1 to the n minus 1, okay, that is an alternator. And so before we try and find what the actual sum is approximately, we might as well see if it converges first, right? Because if it diverges, trying to trap infinity, no, that's not going to happen. So once we get rid of the alternator, what's left? 1 over n factorial. Does 1 over n factorial go to 0? Yes. Do the terms decrease? Yeah, they decrease for all n greater than or equal 1. So this is a convergent alternating series. Now, what is it equal to? Well, We don't know. So let's go ahead and start lifting out some of the terms. It says to use the first 6 terms. So I'm going to call this S sub 6, the 6th term partial sum. And we just start generating the terms, right? So plug in the 1 for n, and what do we get? We get 1, right? Boom. Plus, plug in 2, and we get -1, right, over 2 factorial. I'm going to call this minus 1 over 2 factorial. If I plug in a 3, what do I get? Positive 1 over 3 factorial. If I plug in a 4, I get -1 over 4 factorial. Now, at this point, do we really need to keep looking up at the nth term to generate the next term, or do you pick up the pattern? Yeah, there are 2 types of patterns here. We have the rule of sequence pattern, that is those that generate the term, and then we have, for lack of a better term, I call it the inherent pattern. You have the rule pattern or the formula pattern, but then you have the inherent pattern, okay? And that's going to be important because later on, it might be tedious to keep generating terms by a formula, but once we have the inherent pattern down, we can generate the next term pretty easily. So 1, 2, 3, 4, we need 2 more terms, don't we? Now, without looking at the rule of sequence, what would the next term be? 1 over 5 factorial. And what would the last term be? -1 over 6 factorial. Yeah. And 1, remember then, if we work backwards, 6, 5, 4, 3, 2, this must be 1 over 1 factorial. And it is. It's just 1 though. Okay. So there's the partial sum. Let's go ahead and see what the calculator says that's equal to. Okay. We could do this one of 2 ways. We can either type it in since we've generated it, or we can use the calculator's sigma capabilities. Remember that? All right. So if you have your calculator, great. If not, you want to pull this one up remotely, or you can jump up and grab a calculator. It's up to you. But we do want to learn the keystrokes here. Okay, I got to try loading this one more time. Wow. All right, I'm in business. Okay, so let me show you how to type this in manually since we've generated the terms. I'm going to get 1 divided by 1 factorial. Where do we get the factorial button? I know this is just 1, but I'll go ahead and type it in. Well, it's not the alpha exclamation mark. Alpha window is a good way to get to a lot of common things. Mine only goes through 5. If yours goes further, you can go that way. Here's where everybody can get it. Go to the math button, which is right below the alpha button, and click to the left 1 time, or click to the right thrice. You get to probability. And the factorial button comes about because of probability. It tells us the way to arrange n items, which you can then figure out the odds of picking an item, right? So it's under the probability menu, which is number 4. So there's that. And then we'll go -1 over 2 factorial. Now, we know 2 factorial is 2, so you can expedite your plugin if you want. And then plus 1 divided by 3 factorial. We know what 3 factorial is, right? It's 3 times 2 times 1, which is 6. And then -1 over, what's 4 factorial? It's 4 times 3, it's 24, I think. And then plus 1 over, 5 factorial. I'm not gonna do it in my head. I'm just gonna say 5 factorial. Math probability 4. And you don't need to put parentheses around that. It associates the factorial with the 5. Okay, so this is what I got. 0.633. Okay, so that's your partial sum. So if you want to, you could say this. You could say S, the actual sum, is approximately this. Now, of course, if this were, strictly a calculator question and it asked you for the 6 partial sum, you could also do it this way. You can go to alpha window, which goes to your shortcut, and number 2. Okay, this is nice, number 2. And you can actually just type it in. We're using X instead of N, no big deal. From 1 to 6, right? So we put the upper bound as 6, And then we just have to carefully type this in here, right? So extra parentheses, -1, close to the x minus 1th power, all over x factorial, which is x math probability 4. Okay, so this again is your quick way to get to the answer. 91 divided by 144. Uh-oh, so. Oh, okay, on my partial sum. Okay, okay. Yeah, it was hanging. I remember it was hanging off the side of the screen and I missed it. That's what I call tunnel vision. That's the only bad thing about the iPads. You know, when you zoom in, you forget about what's around. But if you look at your paper, you can always kind of see it in your peripheral. So thank you. I'm glad we did it both ways because we can check, right? 0.63194. You know, that was repeating decimal. I'm going to go ahead and just call it 91 144ths, okay, because that's exact. But anyway, the sum, we know it converges, and it converges approximately to that. Now, here's the question. What's the actual sum? Well, we don't know the answer to that. What is the actual sum? But we know that this number has to be within a certain amount from the actual value, okay? So here's what we could do. We could say then that what is A? So how many terms did we use? 1, 2, 3, 4, 5, 6. So what's the first unused term? The 7. So that's A sub 7, which when you plug it in is 7 minus 1 is 6. It doesn't matter. We take the absolute value of it anyway. So we don't need to worry about the alternator. It's 1 over 7 factorial. Okay. That's the first unused term. Now, what we're saying then is the actual sum has to be within that amount on either side. It's an alternating series. So we subtract to make it smaller, then we add to make it bigger. So we have to look at both sides. So here's what we could say. We know that S is going to fall within this interval, 91 144ths minus 1 over 7 factorial. Okay. And then 91 144ths plus 1 over 7 factorial. That first unused term is your error bound. It's your margin of error, if you want to use statistics term. And it should make sense why the sum will have to be within that amount. That is the next largest term in the entire sum, right? Because the terms get smaller and go to 0. So that first unused term, think of it as like a big brother that's sheltering all the other little terms that are underneath it, right? I got you, little terms. I got your back. I got your front. I got your sides too. I just got you. Right? None of y'all are bigger than I am. I'm the biggest, so I'll protect you. He becomes then the margin of error. You never have? Okay. So let's go ahead and see what that is. I'll type that in here, right? Let's see. I'm going to do this. 1 divided by 7 factorial. I'm going to type that in first. And I'm going to store that as x. Store it as x, just to make it a little bit easier. And then 91 divided by 144 minus x. Boom. This is 0.631746, 0317. I'm just writing out more than 3 decimals, obviously, because I want to be able to compare it. And then I can just hit second enter if I want to, recall it, and go to the plus, right, for your upper bound. 0.6321428571. There you go. I don't know what the actual sum is, but I know it has to live within this interval. Right? So I've trapped it. I know what it is at least to the hundredths place, right? Now we do have the luxury of verifying this because I can actually do math. I gotta keep turning it on. Alpha window number 2. Let's go ahead and go back up here and we'll go from x equals 1 to, we did 6 for the partial sum, but we've done this before. Let's plug in infinity. Oh wait, we can't. So what's a big number? Let's try 100. Yeah, because it's factorial. It's going to grow fast, right? And then we'll type this in again. Alpha y equals. It might have been faster just to recall it from above, but what the heck? To the x minus 1th all over x factorial, x mass probability 4. And going out to 100 terms may take a while. Overflow. See, yeah, it grows. Factorial grows so quickly that it didn't work. So let's, instead of 100, 50? Yeah, let's try. We'll try 75. Let's try 75. Yeah, we might. Yeah, we do.
Do like 20. Do like 20.
20. There you go. There you go.
50 has 68 zeros behind it.
All right, let's try 20. The first 20 terms. There you go. So all I want to show you is that number that we get, does it fall in our interval? Oh, okay. So that's good. I'm glad you did that. You did 50 and you got the exact same number, which means that this number that we see here is the actual part of the number. Yeah. So it only is going to start differing way down the line. So as far as we're concerned, to this many decimal places, this is absolutely correct. Okay, good. Now, does this number fall in that interval? It does. Okay. So back in the day, before these computing devices, they didn't have this luxury, right? It still works. It still works, but they didn't have the luxury of using these computers to do all the heavy lifting for them. But
that's bigger than that.
0.63212 is smaller than 0.63214. Yeah. No, you have to start looking way down the line to compare decimals, and it does kind of cross your eyes a little bit. So yeah, it falls in that interval. So anyway, that's called the alternating series remainder or the alternating series error bound. The error bound is this right here, 1/7 factorial. And here's what we know. Whatever our partial sum is, it's going to fall within the first unused term on either side. Okay? That's pretty easy to remember, right? First unused term. Sweet potatoes. Okay. Comments, questions so far? So good so far, so good? All right. Let's go to example 19. Same thing, but asked a little bit differently. Approximate the sum of this here such that the error of the sum is smaller than 1/1000th. Approximate the sum whose error is less than 0.001. Well, the first thing I want to figure out is, what is the first term in the sequence that is smaller than 0.001? Would you agree? Okay, so let's just start listing them. And when we're looking at absolute values, right? When we talk about the error bound, it's a magnitude, okay? Because we're going to add it and subtract it. So let's just start typing things in. 1 divided by 1⁴. That's the first term. Is 1 less than 1,000th? No. So we're going to have to add more than the first term. Okay, what would the next term be? 1 divided by 2⁴. Is that less than 1,000th? No, so that's not going to be it. Okay, how about 1 divided by 3⁴? Is that less than? No, but we're getting there, right? We're getting there. 1 divided by 4⁴. Is that less than 1,000 now? Still not. No. Okay, no. All right. How about the next term? 1 divided by 5⁴. Hey, we finally got another one that's not less than 1,000. 1 divided by 6⁴. Well, that one I have to write that one out now. That's 0.0007. 1716. Is that less than 1,000? That is less than 1/1000th. Okay, so that ended up being the sixth term, right? This is a sub 6. So we did that kind of by trial and error, right? And luckily, it was only on the sixth term. If it had been on the 60th term, we'd be like, oh, I'm hungry. I got to take a break, right? Yeah, there is. We'll talk about it. But for what y'all are going to be expected to do, they're not going to put it at the 60th term. No, it'll be like within the first 6, 7, 8 terms. So you can do trial and error. Now, we have to finish answering the question. This is the first term. This is the first term, bless you, where the first unused term was less than 1/1000. That means to get the partial sum that is within this amount. Well, do we find, in other words, do I find then S of 5, S sub 6, or S sub 7?
S sub 6. You gotta find S sub 5. S of 6, X of 6.
The error is going to be within the first unused term. This was the first term. So that's going to be the first one that I don't use. So I'm going to find the sum of the first 5. Get it? I'm going to add up the first 5 terms because the 6th term is the first. It's not wrong if you say S of 6 or S of 7. Okay. Right. So I realized that I could have asked this maybe a slightly different way. What is the smallest sum, or what is the smallest sum that is within 1,000? That's probably a better way to ask it, right? What is the smallest sum that's within 1,000? And that would be S of 5. Okay. So when you're going backwards, you got to remember this is the first unused term. So we need S sub 5. So let's just go ahead and say S squiggles S sub 5, which equals. Okay. And now I'll just use the sigma notation. Alpha window, number dose. We'll go to X. Hey, let's do this one a little bit differently first. Go to your mode, and go down to function parametric polar sequential. If you come down here, go over to SEQ. That doesn't mean sequin, that means sequence. Now look what happens if you switch to sequence mode. Whenever you hit the X button, it turns into N. So you can actually use N now if you want. Watch, let's just type it in. Alpha window, number dose, from X, which is now N equals 1. And you're like, now it matches. I feel more better. And then alpha Y equals -1 to the N plus 1. Orale, all over the nth to the 4th. Look at it. It's N.
That's actually just so.
Yeah, it looks cool, right? 0.947539429. Okay, there you go.
I can just type X for that.
Sweet. Now, do we need to switch to parametric mode in order to do this? No, you can leave it in X mode, because as soon as you insert the sigma, your calculator knows that it's not counting by real numbers anymore. It knows to count by natural numbers. So the variable doesn't really matter, but I just thought I'd throw that in there. Now in chapter 7 and 8, that's where we deal with the other two in chapter, and we'll get to that. But that's where we get to the parametric mode, where when you hit X, it becomes T, and the polar mode, when you hit X, it becomes theta. So if you wondered why your X button says X, T, theta, N, it's because that shortcut becomes the variable for that type of function. Okay. Yeah. That's how you get those. Okay. Well, those are the chapter 7 and 8. I'll have to answer that a little bit later. All right. Any questions on the alternating series test? Probably the most important test that we have moving forward. Second only maybe to the ratio test. They can fight it out. Okay. So the ratio test is also very good. So let's move along. Ratio test. This is the last test that you're required to know. I do show you one called the root test just because I like it, but the root test is not on the AP exam. The ratio test is all over the AP exam. Okay. Hello. Here's what the root test says. You ready? Nope. Hi. Oh yeah. Come on in. Absolutely. Come on in. I'm going to pause the recording here. I'm recording, so let me just pause the recording. All right. So the ratio test. Here goes. Allow. In other words, don't argue. Let the series from 1 to infinity of a sub n be a series of non-zero terms. Okay. Doesn't say positive, doesn't say negative. They're just not zero. This is a two-way test. If the limit as n goes to infinity, the absolute value of the n plus first term divided by the nth term. If that ratio is less than 1, then the series converges. Okay. If that ratio is greater than 1, the series diverges. But like the second derivative test, it doesn't always work. If you get a 1, it's inconclusive. Okay. So this is not the limit comparison test. The limit comparison test was a limit ratio of two things, but that's one where you brought your own series or sequence into the fold and you compared them, and the ratio could be one over the other either way. This one says take the subsequent term and divide it by the previous term. That should make sense, right? Like take the fourth term and divide it by the third term. If that ratio is less than 1, as n goes to infinity, that's kind of the same idea of saying it's getting what? Smaller and smaller, fast enough to converge. So that idea should be ingrained in there. And if it's greater than 1, then it's going to get bigger and it diverges. Okay. Now, when do we use the ratio tests? Right here. The ratio test works really, really well when you have things that grow very rapidly, such as factorials or exponential or combinations of them. Okay. So if you see like a radical, a factorial, not a radical, a factorial, or something that looks exponential, the ratio test is a good candidate, or a combination of them. Let's try it out. Example 20. Determine if the following converge or diverge. All right. We're staring at this guy and we're like, okay, it's an infinite series from 1 to infinity. It's a quotient of exponential to factorial. Now, let's do the nth term test. Do those terms go to 0? Yes, because n factorial grows faster than exponential. He's the king or queen of growth, right? So the terms do go to 0. So the nth term test is inconclusive, right? It may converge, it may diverge. Now, what does your intuition tell you? Converges? Yeah, I mean, the top is putting up a pretty good fight trying to counterbalance it going to 0, but n factorial is going to win, right? So it should converge by intuition, but we need to prove it. So none of the other things that we have are going to work here. If I try to pick something to compare it to, the limit comparison test isn't going to work. It's not purely a geometric series because it has the n factorial in it. So when you see a radical, you should be thinking ratio test, right? Hopefully. So here we go. Here's the ratio test. We're going to take the limit as n goes to infinity of the absolute value of. Now, here's how you get the n plus first term. To get the n plus first term, all you do is you replace n in the rule of sequence with n plus 1. So this becomes 2 to the n plus 1th power all over n plus 1 factorial. I'll put both of them in parentheses. That's the n plus first term. All over the nth term, which is just the rule of sequence. Okay. Jackson, they need you. There you go. All right. Is everyone okay with that? How do we find the n plus first term? We just replace all of the n's with n plus 1. Okay. Now we set up a complex fraction. Yeah. So state, change, flip. State, change, flip. The limit as n goes to infinity of 2 to the n plus 1 all over n plus 1 factorial times n factorial all over 2 to the n. And you could actually go straight to that step if you want to, okay? If you, after you do enough of these, you can get comfortable. You're like, oh, it's just gonna be a complex fraction. So state, change, flip. Kind of like what we did with the limit comparison test. Now all we have to do is simplify, okay? Simplify. And this is why I like the ratio test. It's fun. It's fun to simplify, right? So here we go. We got the limit as n goes to infinity. Let's go ahead and do the factorials first. We did this earlier, right? Which is bigger, n plus 1 or n? N plus 1 is bigger. So you start with the larger one that's in factorial and you write it recursively until it matches the other one. So n plus 1 factorial is n plus 1 times n minus 1 times n minus 2. But I'm going to stop at n. Why? Because that's what's in the numerator. And so then I'll just rewrite the one that's up there. So that takes care of this. Yes. I just wrote the bottom recursively. Now let's do the top as well. 2 to the n plus 1 is bigger than 2 to the n. Well, I can write 2 to the n plus 1 as 2 to the n times 2 to the 1th. Yes. And that's all over 2 to the n. So that takes care of that. What we're trying to do is write them in terms of each other because we want things to divide out. And do things divide out? Indeed. Those are gone. And These are gone also as well, additionally too. So that's the limit as n goes to infinity. Let's see what's left. What's left on the top after all that? Well, there's a 2 up there, right? And in the bottom, there's n plus 1. Oh, and now it's a, yes. Oh, yeah. So off to the side here. Remember, if I had like n plus 3 factorial all over n minus 1 factorial. We did this kind of just on a warm up one day. If you want to simplify factorials, start with the one that's larger and start writing it recursively. N plus 3 is larger. So I'm going to write the top as n plus 3 times n plus 2 times n plus 1 times n plus 0 times n minus 1 times n minus 2, so on and so forth, right? Times n minus 3 times n minus 4 times ... times 3. We're eventually going to hit 3 times 2 times 1. That's what that means, okay? But I'm not going to write it all the way like that because the bottom is n minus 1 factorial, right? So what I'm going to do is I'm going to be like, oh, I got it right there. So I'm just going to package all those up and call it n minus 1 factorial. And now what happens? All of those factors down the line divide out. Does that make sense? Okay, good. Bueno. Excellent. You got to understand this. I want you to understand this. This is fun. These are good ideas. Thinking through this is good for you. Any other questions before we proceed?
Then
Yeah.
after the n minus 1, there's just like an exclamation point, like right after, like there's an n exclamation point.
Oh, right. The n minus 1 factorials are completely gone. So the exclamation points are gone. And all we're left with are those residual factors. Okay. Yeah, there's no more exclamation point. Just think of the exclamation point as being a placeholder for all the other factors that are going to be the same. They all divide out to give you 1. Okay. So that's what we did over here. I started with n plus 1 and I wrote it as n plus 1 times n. And then I stopped there because I had n in the top. So I tied it off with that factorial. And now both n factorials are gone, leaving just an n plus 1. And then, of course, with the exponentials, you could just use the rule of exponents, right? When you divide and the bases are the same, you subtract. So n plus 1 minus n is just 1. Or you could just write it like I did, 2 to the n times 2, and your 2 to the n's divide out, okay? So what that did is it got rid of the exponents that were n, and it got rid of the factorials. And that's what should happen when you do the ratio test, okay? We got rid of our factorials, and we got rid of our exponents. And now we got down to this little dude. This is easy, right? As n goes to infinity, what does 2 over n plus 1 approach? 0. So you can say that that's 0, right? Because the top stays at 2 and the bottom gets infinitely large. And now we'll compare it to the requirements of the ratio test. The ratio test says if that ratio is less than 1, the series converges. If it's greater than 1, it diverges. If it's 1, inconclusive. Well, 0 is what? Less than 1. And that right there, that's your argument. This is your argument. That simple little inequality says that you understand what the test is about. And now you're going to say, so let's give this series a name. What do you want to call it? Let's call it Big F for Friday. Big F. So Big F does what? Converges. Yeah. By the ratio test. Fun, right? So your intuitions were correct, right? Again, always think back to the old harmonic series, 1 over n. That series diverges. But if the exponent is anything bigger than 1, like 1.00001, it'll converge. So that's kind of the requirements. So you can keep that idea. If it grows faster in the bottom, significantly faster, it'll pull the terms to 0 fast enough for the sum to converge. Okay, cool. Well, let's look at B. Let's look at B together. If you looked at B, I don't see any factorials, do you? But I do see kind of some exponential pieces, which could be geometric, but then I have this polynomial piece in there. So if you were to compare it to a series, would you compare it to 3/2 to the n? Or would you compare it to n squared? What would you compare it to? Well, before you compare it to anything, never not first do what? Nth term test. Nth term test. What happens in the top when you plug in infinity versus the bottom? Which one grows faster? The top grows faster. It's 3 to the n instead of 2 to the n. Oh, and by the way, he's got a helper up there, n squared, to boost him. So do the terms in the sequence go to 0? No. Okay. So you can say the limit as n goes to infinity of n squared times 3 to the n plus 1 all over 2 to the nth equals infinity, which is not 0. So let's call this guy L for loser. So L diverges by the nth term test. I don't want to call him loser. April Fools, let's call him E for excellent. Excellent loser. Right? He has good sportsmanship. Got it? Now, what if you forget it to do the nth term test? And you're like, oh, it's not a one-off, so I can't compare it to anything. It has exponentials in it with some other garbage. Maybe I'll try. Let's try the ratio test. It is a two-way test after all. Can we use the ratio test here? Let's try it. If we do, we should get the same result, right? Right, good. So let's try the ratio test. The limit as n goes to infinity of the absolute value. I love this. Getting the n plus first term, you just replace n with n plus 1. So instead of n squared, it's n plus 1 squared. And now be careful here. It's 3 to the n plus 1, which is what? N plus 2. All over 2 to the n plus 1. All right, now I'm going to divide that by the given nth term, but it's also a fraction. So this is where I'm saying, hey, you could do stay, change, flip. That's times 2 to the n all over n squared times 3 to the n plus 1. Okay, now on your own, without me guiding you, go ahead and simplify that down as much as you can. Okay. There's no factorials, but we still have some exponential pieces to clear up. And I'll do the same thing. Ratio test. I love the ratio test. I love simplifying that absolute value quotient after we set it up. It's fun. It's fun. It's a little different, right? Feels like we're just frolicking through the problem. Now, if you notice how I did that, I showed that step with blue and purple here. And the polynomial parts, you don't have to expand out the n plus 1. You can leave the polynomial parts alone, okay? It's the factorials and the exponential pieces that you're going to want to simplify. Now, 3 to the n plus 2 is the same as 3 to the n times 3 squared. And 2 to the n plus 1 is 2 to the n times 2 to the first. And 3 to the n plus 1, same thing. So Once you do that, your 3 to the n's will divide out and your 2 to the n's will divide out. And you're just left with numbers with the polynomials. So in the top, you're left with the number of 9, which I brought out front. And the bottom, you're left with 2 times 3, which is 6, which I brought out front. Now, if you were to expand the n plus 1 squared, the first term would be n squared times 9, which is 9n squared. And on the bottom, you have 6n squared. Now they're both squared. It's just leading coefficient over leading coefficient, right? So that would be 9 over 6, which is 3/2, which is 1.5, which is greater than 1. Therefore, so E, the excellent loser, diverges by the ratio test. And it's the same result as the nth term test, but it's a little bit more work, right? It is a lot more fun, but it's a little bit more work. Okay. And when you have a little bit more work on any kind of exam, time is a sacred commodity. So taking time to do something one way that's longer, it comes at an opportunity cost of using that on other problems. And the more steps in the problem, the more likely you're going to do it. I'm pretty notorious for smashing mirrors. No, making careless mistakes, right? Making careless mistakes. All right. How do y'all like the ratio test? Pretty good? I like it. I like it. Yeah, you do one by yourself. Oh, well, let's let you do this one by yourself. Let's flip this one around. Flip it around. Let's do from n equals 1 to infinity of 3 to the n all over. Let's do the, I'm changing it even. Let's do, yeah, let's just do 3 to the n over n plus 1 factorial. Go ahead and do that one. We'll call this B2. Yeah, we'll talk about C. Yeah, but you can use the space for C if you want to do that one. Okay, I'll pause the recording so y'all can chew on it on your own. All right, so here, I'm just going to, for the sake of the video, here is the B2 converges by the ratio test. And if you flip the ratio, it diverges by the nth term test. So remember, never not first for a limit, direct substitution. But for testing a series, whether it converges or diverges, never not first, nth term test. Saves time, saves money, saves possibility of errors. Okay, the root test is not on the AP exam, but I like it. I like it. It's not my favorite, but I still like it. Medium. Here's what it says. It's very similar to the ratio test, not just because it starts with an R as well, right? But the inequalities match up. Okay. The series will converge if the limit as n goes to infinity of the nth root of the rule of sequence, the magnitude of it. So if it's an alternating series, throw the alternator out. The absolute value. If you take the nth root of the rule of sequence as n goes to infinity and it's less than 1, the series converges. Otherwise, the series diverges if the nth root of the rule of sequence is bigger than 1. And like the ratio test, if it equals 1, it's inconclusive. So when would the nth term test be useful? Or the root test. I'm sorry. When would the root test? My glasses are upside down. I can't concentrate. When would the root test be beneficial to use? How would you spot it?
If it was e to the 2n over n to the power.
Yeah. If you can write your entire rule of sequence as a power of n, that's when the root test would be beneficial. Like on a geometric series, right? On a geometric series, like 2/3 to the n, you can use the geometric series test, but the root test works, right? Because what's the nth root of 2/3 to the n? Yes, 2/3. Maybe I should write it down. I shouldn't just pontificate math out in the open. For instance, what if I have from n equals 5 to infinity of 3 times 2/3 to the nth power? Well, you could bring the 3 out front, just like an integral. And now we have 2/3 to the n. I could use the geometric series test, right? The absolute value of r is 2/3, which is less than 1, converges. But I can also use the root test. The limit as n goes to infinity of the nth root of 2/3 to the n. That equals what? 2/3. Yes, thank you. Yeah, oh, it's still up front. Sorry, I forgot to bring it along for the ride. He was in the back of the truck and I hit a bump and he jumped out. Sorry. You brought him back in. Very good. I'm sorry. So it equals 3 times 2/3, which is actually 2. Okay. Wait, that didn't turn out right. Wait, that didn't turn out right. The 3 is outside the test. The 3 is outside the test. So this is going to be 3 times. Well, let's just get rid of 3. Let's just get rid of 3. All right, he's out front.
We got rid of it.
Yeah, but I'm going to just say, hey, if the series converges, then I know 3 times that's going to converge. So if I do the limit test, the ratio test inside, that it does equal 2/3. Okay, and 2/3 is less than 1. So the series converges by the root test. Okay, so it works for geometric series. Now, do you want to use the root test instead of the geometric series test? No, heck no, not at all. Because the geometric series test is shorter, right? And you can also find the exact value. Yeah, más mejor que bueno, sí. All right. If the entire rule of sequence can be written as a power of n, the root test is hard to beat. Let's try this one out. Example 20. Yeah.
What is this one good for then? Oh, okay, yeah. E2.
Yeah. We have Aleph functions here. See that end to the end? Aleph functions probably not going to be on the AP exam. Okay. Unless it's, well, log diff isn't on there either. So for y'all, the factorial is probably the fastest growing. But we do have the king's wife, right? The queen, n to the n. So the nth term test, who grows faster, exponential or Aleph functions? Aleph functions, right? So the nth term test is inconclusive. You could use the ratio test, but if you use the ratio test, how are we going to simplify n plus 1 to the n plus 1? That's going to be, if you try it, it's going to be hard to divide it out. So now you're like, hey, there's only 2 factors, one on the top and one on the bottom, and they're both factors of n. So I can write this like this. 1 to infinity, I can write this as e squared over n all to the n. Okay, because I have this property that says a over b to the nth power is a to the n over b to the n. So you can verify, if you distribute that n exponent back in, you get e to the 2 times n over n to the n. Ah, niceness. So now I could do this. So the limit as n goes to infinity of the nth root of e squared over n to the n. Well, what happens there? He gets e squared over n. Yeah. And I still have the limit there. And now e squared is a number, right? And as n goes to infinity, what happens to this ratio? It goes to 0, right? Which is less than 1. So let's call this guy G, right? So G converges by the root test. Okay. Probably not going to have this one on the AP exam, but in life, maybe, right? I want to prepare you. Yeah. No. If you know it's positive, you don't have to take the absolute value. The only thing the absolute value really is there for is for you to remember that if it is an alternating series, just like on the limit comparison test, we throw the alternator out. Okay. You just want to make sure that it's a positive thing under the radical. Okay, does that make sense? Good one. It's a good one, right? It's kind of nice to have another tool in your tool belt. All right, how about this one? Never not first. What do we do? Nth term test. And if we take the limit of the rule sequence, if we take the limit inside, we get 3/2, but then it's to the nth power. What is that? Is that going to converge? Is that going to go to 0? No. Powers of 1.5 get bigger and bigger and bigger. So this is actually going to diverge by the nth term test. But Can you convince yourself of that? Or maybe if you're not convinced, it's not geometric, but the whole thing is immediately a power of n. So let's just take the limit as n goes to infinity of the nth root of the whole dude. The whole dude. And now what is the nth root of something to the nth power?
3n+4.
The n's essentially, if you write it as fractional exponents, right, you get n to the 1 over nth power. And when you multiply, you get n over n, which is 1. All right, now, what is this approach? This should be a 2 down here. I don't know why I turned it into 3. Yeah, this turns into 3/2, which is greater than 1. So let's call this P. So P diverges by the root test. Was that our bell? Are we done? Oh man, time flies when you're doing calculus, because calculus is fun, right? Okay, fun, easy. All right. Well, we all we have left to do is to put it all together and practice, practice, practice. So there is a way to remember all the tests called parting C, like Moses. Okay, it's not necessarily a flow chart because nth term is always first, but parting C will help you remember them. P series for parting, A for parting, ratio test for parting, telescoping series for T. We didn't really do that. I'll talk about that next time. I for integral test. Did we do the integral test? We did, yeah. Oh, we did it on the video, yeah. Nth term test. Okay. Parting, see you later. Ketchup, not mustard, but ketchup.